We are going to work our way through homework 5 here, and homework 5 is on exponential functions and logarithms. And really, about the first 2/3 of this assignment should be review. So it's a review of logarithms and properties of logarithms. But once we get down far enough into the section, we get to questions where it's going to start asking us about derivatives. So what's the derivative of natural log of x, or what's the derivative of e to the x? So the real calculus doesn't get started until we're quite a bit further into this assignment. But let's start with question number 1. What is log base 3 of 81? So 3 to the what power is 81? Well, 3 squared is 9. 3 cubed is 27, right? 3 times 3 times 3. And 3 to the 4th power is 81. So we put 4 here. Okay, now question 2 is log base 2 of 1/8. What does that equal to? Well, if this had said 8 instead of 1/8, the answer would be 3, right? 2 to the 3rd power is 8. But isn't it 2 to the negative 3rd power that would be 1/8? In fact, why is the answer negative 3? Why is the answer negative 3? Well, 2 to the negative 3rd power, this to this power, is the same thing as 1 over 2 to the positive 3rd, right? That's just how you deal with a negative exponent, right? 2 to the negative 3rd is the same thing as 1 over 2 to the positive 3rd, but that's just 1/8. So 2 to the negative 3rd is 1/8. So that's why we put negative 3 here. This to this power is equal to this. Now this one says, what is log base 23 of 1? Okay, what does that equal to? Well, 23 to the what power equals 1? Well, isn't it 23 to the 0 power, right? Isn't anything to the 0 power 1? Now, question 4 has a whole bunch of different parts to it. So, for example, part A, what is log base 3 of 9? Well, that's going to be 2, right? 3 squared is 9. Okay, part B, well, that answer is also going to be 2. What's log base 6 of 36? Well, it should be 2, right? 6 squared is equal to 36. Okay, now part C, what's log base 4 of 64? Well, 4 squared is 16. 4 to the 3rd power is 64. Okay, so you can work your way through these questions. I'm going to move on to the next one here. This one is similar, but it has log base 4 of 1/16. Well, notice, isn't that going to be negative 2? 4 to the negative 2 power is the same thing as 1 over 4 to the positive 2, which is 1/16. Okay, now this one here says, what is natural log of 1? Okay, this is ln of 1. So really, it's log base e of 1. So ln means log base e. So the question is really e to the what power would equal 1? Well, e to the 0 is equal to 1. By the way, this is not the word in. Every now and then, I'll have a student do this on a homework and they have to type in logarithm, like ln, natural log, and they'll type the word in, like capital I and N, but it's actually ln, right? Lowercase l. That's a lowercase l. It's not a capital I. Okay, what's natural log of e cubed? Well, again, there's this invisible e here. E to the what power would equal e cubed? Well, e to the 3rd equals e cubed. Right? Remember, natural log is log base e. So there's an invisible e there. Okay, now what about log of 0.00001? Well, this is log base 10. Remember, if you see the word logarithm written without a base, the base is assumed to be 10. So 10 to the what power is equal to this? Well, this is, let's see, that would be 1/10, 1/100th, 1,000. I think this is 1/1,000,000th. Right? So I believe, in fact, if we move the decimal place of 1, 2, 3, 4, no, it's actually 1/100,000th. So I believe this would be -5. In fact, you could even type this into your calculator. Your calculator should have a log button, and that means log base 10. It should also have a natural log button. But the question is really 10 to the what power equals this? Well, 10 to the -5th power. All right, now this next one says find log of 1,000,000 and do not use a calculator. So the base here is 10, right? If you see the word log written without a base, it's assumed to be 10. So the question is 10 to the what power is equal to 1,000,000? Well, isn't it 10 to the 6th power, right? 10 times 10 times 10 times 10 times 10 times 10, right? Wouldn't that be a million? Now, by the way, most calculators don't have a log base 6 button. They have two buttons related to logarithms. They have the log button, which means log base 10, and they have a ln button, right, which means log base e or natural log. So what about this? 6 to the what power equals 136? Well, wouldn't it be negative 2, right? 6 to the negative 2 power is equal to 1 over 6 squared, right? 1 over 36. What about this? Well, 2 to the what power equals 1 half? Well, isn't it 2 to the negative 1 power? 2 to the negative 1 power would be 1 over 2 to the positive 1, right? 1 over 2. How about this one? Log base 2 of the square root of 2. All right, now how do we do this one? Well, 2 to the what power equals the square root of 2? Well, isn't it 2 to the 1 half power? 2 to the 1 half power is like the square root of 2. So you could do a similar thing, like what is log base 7 of the square root of 7? Well, wouldn't it also be a half, right? 7 to the 1 half power is the same thing as the square root of 7. Now, what if it were like log base 19 of the cube root of 19? Well, wouldn't this be 1/3, right? 19 to the 1/3 power, that's the cube root of 19. Right? So the fact that we have a square root of that number, that gives us the 1 half and 1 half here. If it were a cube root like this, we would get 1/3. So this is a half. This one says, find the indicated value of the logarithmic function. What is natural log of e to the 6th? So the question is e, right? So there's, again, the invisible e here. E to the what power would equal e to the 6th? Well, e to the 6th equals e to the 6th. In fact, you could do this one on a calculator. Just type in natural log of e to the 6th on a calculator. It should give you 6 as your answer, but you don't need to use a calculator, of course. Okay, same thing here. E to the what power would equal e to the negative 5th? Well, e to the negative 5th. Right? E to the negative 5th equals e to the negative 5th. Okay, now this next one is very similar. What's natural log of the 4th root of e? Well, this one is kind of similar to these ones right here. The question is natural log of the 4th root of e. Well, again, here's there's an invisible e down here. So these ones have numbers 2, 7, 19. This is log base e. So the question is e to the what power would equal the 4th root of e? Well, isn't it e to the 1/4 power? E to the 1/4 power is the same thing as the 4th root of e. Right? If this were a square root, we'd have 1 half there. Or if it were a cube root, we'd have 1/3. So we put 1/4. Oh, by the way, it says type an integer or a simplified fraction. If I were to type 0.25, so 1/4 is the same as 0.25, would that give me the correct answer? Actually, I think it would mark it wrong because 0.25 is not an integer. Remember, an integer is a whole number. Okay, and it's also not a simplified fraction. Right? So you can't type 0.25. So be careful to read what's in blue here. In fact, if you were to type this into a calculator, it would probably give you 0.25 as the answer. But the answer is 1/4 if we're going to type an integer or a simplified fraction. So 1/4 is a simplified fraction. It's not an integer. But that's why 0.25 would not work there. Okay, now this one says write the logarithmic equation in exponential form. So we have a logarithmic equation here. Log base 2 of 8 equals 3. So what this means is 2 to the 3rd power is equal to 8. Okay, so that's what we're going to do. Right, is 2 to the 3rd power is equal to 8. Similar one right here. This means 10 to the 3rd power equals 1,000. Okay, so that's what you put down here. 10 to the 3rd equals 1,000. Now this one says W to the 17th power is equal to Q. Okay, so W to the 17th is equal to Q. Here we have, again, the invisible e here. ln means log base e. This is e to the 7y power equals negative 3x. Okay, so before you start looking at the answers down here, just look up here. What we want to rewrite this logarithmic equation in exponential form. So what this means is e to the 7y is equal to negative 3x. So let's see, which one do we get here? That's this one. Now this one has an exponential equation, 6 squared equals 36, and we want to rewrite it as a logarithmic equation. So we have 6 to the 2 equals 36. So notice, isn't that part B? We have 6 to the second power equals 36. So whenever you're looking at log base something of something equals something, it means this to this power equals this. So 6 squared equals 36. This one would say 36 squared equals 6. So that's not right. This one would say 6 to the 36th power equals 2. That's not right. This would say 2 to the 6th power equals 36. That's not right. This is the correct one here. Here we have 10 to the t equals p. So notice, isn't that this one here? 10 to the t equals p. By the way, this says log base 10. You actually could just write it without even writing the 10 there. You could just write log of p equals t. Because when you write log without a base, the base is assumed to be 10. So we could just write log of p equals t. So that would mean 10 to the t equals p. Here we have 6 to the 7x equals y. Well, notice, isn't that this one? 6 to the 7x is equal to y. This to this power equals this. All right, now here we actually have to use a calculator. This one says, find the logarithm using the change of base formula. So log base 4 of what would equal 15? Well, notice 4 to the 1 power would be 4. 4 squared would be 16. So 4 to the what is going to give us 15? It's got to be like 1 point something. It's got to be pretty close to 2, maybe just a little bit less than 2. Well, how could we figure this out? Well, even with a calculator, how can you figure it out? Because your calculator likely won't have a log base 4 button on it. So how do we do log base 4 of 15? Okay, so how do we do this one? Well, we're going to need to use the change of base formula. That we can change our base here to any base that we want. We can write log base 4 of 15. This would be the same thing, for example, as log, let's change it to base 7. Log base 7 of 15 divided by log base 7 of 4, right? It turns out the change of base formula says this is correct. Now, why would we want to change it, though, to log base 7? Because we don't have a log base 7 button on our calculator any more than we have a log base 4 button. So usually we change it to a base 10 or a base e. So what we can do is rewrite this as log base 10 of 15 divided by log base 10 of 4. Okay, or you could do natural log of 15 divided by natural log of 4. And when you do this on a calculator, by the way, we want to round our final answer. In fact, I think it says round to 4 decimal places as needed. We want to round our final answer to 4 decimal places, but don't just do this one and round it to 4 decimal places and do this one and round it to 4 decimal places, then divide it, because you're doing too many roundings. Your final answer might be off. In fact, if you're going to do this one and this one, I'd round this to maybe at least 6 or 7, use at least 6 or 7 decimal places here, and same thing here. And then when you divide it out, it should be accurate to 4 decimal places. But I think it's best to just type it all in at once into a calculator. Log 15 divided by log 4. In fact, there's log 15. You could round it to 4 decimal places if you want to get 1.1761. But the problem is, if you did the same thing with log 4 and only rounded it to 4 decimal places, your final answer is not going to be accurate to 4 decimal places probably. It might only be accurate to 3 decimal places, let's say. So just do it in one step. So log 15 divided by log 4. And notice that's our answer. So what is this rounded to 4 decimal places? Well, it's 1.9534. Okay, and we keep that a 4. We don't round it up to a 5 because the number after it is a 4. It's less than 5. So 1.9534. If the number after that first 4 was like a 6 or 7 or something, we'd have to round this 4 up to a 5, right? So 1.9534. By the way, we would have gotten the same exact thing if we typed ln of 15 divided by ln of 4. Now, ln of 15 is not the same as log of 15, and ln of 4 is not the same as log of 4. They're different decimals, but that ratio, the ratio here, this log 15 divided by log 4 is the same thing as natural log of 15 divided by natural log of 4. Notice we get the same answer here. Okay, you can do the same thing here. What's log base 8 of 12? Well, 8 to the what power is equal to 12? Well, again, do like natural log of 12 divided by natural log of 8 and round your final answer to 4 decimal places. Now, here I did this and I got 1.19498. Well, that 9, that has to round up, right? Because the one after it is an 8. So it's actually 1.19. I should put 50, right? Okay, because I don't want to round to 1.1949 because that 9 should go up because the number after it is bigger than 5. So 1.1950. Now, this next one is similar to something that we did in a video, and this has to do with the number e. Okay, what is the number e? Well, remember, if you take 1 plus 1 over n to the nth power, and you put large values of n in, it's going to get closer and closer to this number that we're calling e. In fact, that's really the definition of e. So we're going to fill in this table. So we fill it in over here. They filled in the first number. So they did 1 plus 1 over n to the nth power. So 1 plus 1/10 to the 10th power. And they got this number. And it says round to 5 decimal places. Now we want to try it with 100. What's 1 plus 1 over 100 to the 100th power? So we can type it in 1 plus 1 over 100 to the 100th power. Okay, notice we get 2.70481. So it said round to 5 decimal places, so 2.70481. Now, another way to do this, 1 plus 1/100th, isn't 1/100th like 0.01? So this would be like 1.01 raised to the 100th power. Okay, now the next one's going to be 1.001 raised to the 1000th power. And the one after that's going to be 1.0001 raised to the 10,000th power. Okay, and notice these numbers are going to start getting closer and closer to that number e. Okay, in fact, the bigger the number we plug in, the closer this is going to be to e. But again, round these to 5 decimal places. So let's do the first one, 2.70481. Okay, and then go on down and fill in the rest of the chart all the way up to n equals 10 million. Now this one says rewrite the expression as the sum and or difference of logarithms without using exponents. Simplify if possible. So notice we have a quotient here, log base 14 of 17/5, 17 divided by 5. Now the quotient property of logarithms says that we can rewrite this as log base 14 of 17 minus log base 14 of 5. So it's this one, log base 14 of 17 minus log base 14 of 5. Okay, this one is similar. We have log base 5 of x to the 7th y squared over 4. So we want to rewrite this. Okay, rewrite the expression as the sum and or difference of logarithms without using any exponents and simplify if possible. Okay, we have log base 5 of this over this. So we have a quotient inside here. We can use the quotient property of logarithms. This is log base 5 of the top minus log base 5 of the bottom. We have log base 5 of x to the 7th y squared minus log base 5 of 4. Okay, now what about this one here? Well, we have a product in here, log base 5 of x to the 7th times y squared. So we can rewrite this as log base 5 of x to the 7th plus log base 5 of y squared. And then we still have this minus log base 5 of 4 on the end here. Okay, now what can we do at this point? Well, here we started out using the quotient property of logarithms to break it apart into the subtraction. Here we use the product property of logarithms to break it apart into the sum. Now we're going to use the power property to bring the 7 out front and to bring this 2 out front. So we can rewrite this as 7 times log base 5 of x plus 2 times log base 5 of y minus log base 5 of 4. Okay, and I believe that's this one right here. Now, you might be able to do all that in your head in one big step, but I think it's probably best to write it out like I did. And then this is the answer. Okay, this one is similar, log base 4 of the square root of 13 over 10. Okay, so how do we do this one? We're going to rewrite it since we have a quotient here. We're going to rewrite this as log base 4 of the square root of 13 minus log base 4 of 10. Now, the square root of 13 is the same thing as 13 to the 1/2 power, so we could rewrite this as log base 4 of 13 to the 1/2 power minus log base 4 of 10. And then the 1/2 can come out front, right? That use that power property of logarithms. So we can rewrite this as 1/2 log base 4 of 13 minus log base 4 of 10. So there's 1/2 log base 4 of 13 minus log base 4 of 10. This is the correct answer. So again, you might wonder, where's that 1/2 coming from? Well, that was because of the square root of 13, right? That's 13 to the 1/2 power. So you break it apart first using the quotient property, right? Since we have a division there, so we get a subtraction. That's why we have this minus right here. And then we take the 1/2 out front for the square root of 13 one. So again, you might be able to get from here to here all the way in your head in one step, but it's probably better to write it out like I did. Now, this one is really just the opposite. It says rewrite as a single logarithm. So here, it's all broken apart, and we want to put it back together. So we have 3 times log base a of q minus log base a of r. Okay, 3 times log base a of q minus log base a of r. Well, what is this equal to? Well, we can rewrite this by taking the 3 and making it an exponent right here. So we're not going to do the subtraction part and turn it into a quotient just yet. We're going to take the 3 and move it up here. We can write this as log base a of q cubed minus log base a of r. Okay, and now we have a difference of logarithms, so we can rewrite this as a quotient, log base a of q cubed over r. Right? Isn't that what the quotient property would say? Log base a of this, isn't it the same thing as log base a of the top minus log base a of the bottom? So this is log base a of q cubed over r. And again, you might be able to do this in one step, going straight from here all the way to here without doing this kind of intermediate step. But I think it's better to do this intermediate step first. You're probably less likely to make a mistake. So it's this one right here, log base a of q cubed over r. I know you could just guess on these things and keep guessing until you get it correct, but make sure you really understand these problems before moving on any further. All right, now this one we have to solve for x. We have log base 3 of 5x minus 9 equals 1. We want to solve this for x. So what value of x is going to make this true? Okay, log base 3 of 5x minus 9 equals 1. Well, doesn't this mean this to this power equals this? So doesn't this just mean 3 to the 1 power is equal to 5x minus 9? Right, we just rewritten this logarithmic equation. We have this to this power equals this as an exponential equation. Okay, so 3 to the 1 power, though, is just 3. So we have 3 equals 5x minus 9. Now we can add 9 to both sides, and we get 5x is equal to 12. Okay, we added 9 to both sides. Now divide both sides by 5. So divide by 5. And we get x equals 12 fifths. Okay, so we could write 12 fifths, or that's really 2 and 2 fifths. So 2.4 would be what it is as a decimal. So 12 fifths or 2.4. Okay, now it says type an exact answer in simplified form. Use a comma to separate answers as needed. Well, we only have one answer. And the question is, which could we write here? Well, it doesn't say to like type an integer or a simplified fraction or something like that. If it said type an integer or a simplified fraction, then we would definitely want to use 12 fifths. Okay, because that's a simplified fraction. We could not do this because that's neither a simplified fraction nor an integer. In fact, neither of these answers is an integer. An answer is just not an integer, right? Not a whole number. But since it didn't say to do that, 2.4 would be totally fine. 12 fifths or 2.4. That's right, 12 fifths. All right, what about this one? Log base 3 of x plus 1 minus log base 3 of x is equal to 3. Now, this one is a little different than the previous one because we have two different logarithms here. So we don't just have log base something of something equals something. So in the previous problem, that's exactly what we had. We had log base something of something equals something. When it's in that form, you can just do this to this power equals this. But for this problem, it's not in that form. So how can we do what to the what power equals what, right? How do we do that? Well, we're going to combine these two logarithms here using the quotient property, right? Notice we have a difference of logarithms. We can rewrite this as log base 3 of x plus 1 over x, right? This over this, and that will equal 3. So I've just rewritten this left-hand side using the quotient property of logarithms. Now it's of the form log base something of something equals something. So we can rewrite it as this to this power equals this. So we have 3 cubed is equal to x plus 1 over x. Or in other words, 27, that's what 3 cubed is. By the way, 3 cubed is not 9, right? That'd be 3 squared, right? 3 cubed is 3 times 3 times 3 is 27 equals x plus 1 over x. Now, how do we solve this for x? Well, let's multiply both sides by x to get rid of this fraction here. So if we multiply by x, notice these go away. And what you're left with is 27x is equal to x plus 1. Okay, now how do we solve this? Well, we subtract an x here, right? We have 27x equals x plus 1. So this is really 26x is equal to 1. And now if we divide both sides by 26, we're going to get x equals 1 over 26. And you could write that as a decimal, but it's probably some crazy long decimal that probably repeats and everything. So, but let's just leave it as 1 over 26. In fact, it says type an integer or a fraction. So we could not write a decimal here. Okay, now the next one is very similar. Now, what is the base on these logarithms? It's actually base 10. So you'd rewrite this as log of 6x plus 1 divided by x minus 3 equals 1. And then what is your base? So and then you'd have it in the form log base something of something equals something, right? Your base, though, would be 10. So it'd be 10 to the 1 power equals, and it would end up being 6x plus 1 divided by x minus 3. Okay, and then you would solve that. So I'll let you try that. Now this one's a little easier because it's already log base something of something equals something. So you'd write it as 4 squared equals this. So basically 16 equals 9x minus 4, and you'd solve that for x. This one's very straightforward, very simple. We have 2 to the 4th power equals x, right? Well, what's 2 to the 4th? Well, 2 times 2 times 2 times 2 is 16, right? So the solution would be 16. Okay, now this one's very similar, but we have log base 2 of x equals negative 4. So what's 2 to the negative 4th power would be x. Well, 2 to the negative fourth is the same thing as 1 over 2 to the positive fourth, right? 1 over 16. And again, it says type an integer or a fraction. So you wouldn't want to put the decimal for 1/16, right? Because that's the decimal would not be an integer, right? Or a fraction. Now it says solve for the variable without using a calculator. Well, again, we have an invisible e here. So this is ln. And again, remember, this is not the word in, in, right? This is ln, logarithm. Natural log is what it means. We have e to the sixth is equal to x. Okay, so our answer is e to the sixth, right? E to the sixth is equal to x. So x equals e to the sixth power. Okay, now that's an exact answer in terms of e. You could try to write out e to the sixth on a calculator and just type it out, be some crazy long decimal, but it wants an exact answer in terms of e. It doesn't want a decimal approximation. All right, well, the remaining problems have to do with derivatives that involve e to the x and natural log of x. So notice we have here, differentiate the following function. F of x equals -9 plus 3x plus 7 e to the x. Well, the derivative of -9, of course, is 0. The derivative of 3x is 3. And the derivative of 7 e to the x. Well, remember, the derivative of e to the x is just e to the x. So the derivative of 7 e to the x is going to be 7 e to the x, because remember, the derivative of a constant times a function is just the constant times the derivative of the function. So our final answer here should just be 3 plus 7 e to the x. The next one involves finding a derivative that involves a logarithm. So we have f of x equals -6 natural log of x plus 7x squared minus 8. Now remember, the derivative of natural log of x is just 1 over x. So the derivative of -6 ln of x should be just -6 times 1 over x. Okay, or another way of saying that is just -6 over x. All right, so we get -6 times 1 over x, or in other words, we could just write it as -6 over x. And then plus, well, the derivative of 7x squared is 14x. And of course, the derivative of -8 is just 0. Okay, this one is very similar to the previous one, so we'll move on. This one is also similar here, but let's actually just do it. The derivative of natural log of x is 1 over x. And then plus, well, the derivative of 2 e to the x will be 2 e to the x. And the derivative of 3x squared is just 6x. So we have -6x. Now this next one says find the derivative of f with respect to x of this function. F of x equals natural log of x to the 11th. Now later on, we're going to learn something called the chain rule, which will allow us to take derivatives of really natural log of anything. But for this one, how can we do it? Well, the idea here is we're going to simplify this function. In fact, here's our function, natural log of x to the 11th. But remember, the power rule for logarithms says we can bring this 11 out front. So we have 11 times natural log of x. And now we're going to find the derivative. So now we're going to put f prime of x. What's the derivative of this? Well, the derivative of 11 times natural log of x is going to be 11 times 1 over x. Or in other words, just 11 over x. Okay, so here we simplified this first and brought the 11 out front and wrote it as 11 times natural log of x. And then we took the derivative of that. Okay, and the next one is similar. In fact, we could probably do this in our heads here. We can take this 7 out front. Now, it'll multiply by that 5, so we're really going to have a 35 out front. So this is really 4x minus 35 times natural log of x. Okay, and the derivative of 4x will just be 4. And then minus, well, what's the derivative of 35 natural log of x? Well, it'll be 35 times 1 over x, or just 35 over x. Okay, you might need to write that one out, but the idea, again, is you use the power rule to bring the 7 out front. So the 7 multiplies by the 5 to get 35. This one says, first use appropriate properties of logarithms to rewrite f of x, and then find f prime of x. So we have f of x equals 4 times natural log of 12 over x. Well, remember the quotient property of logarithms says that we can rewrite this natural log of 12 over x as natural log of 12 minus natural log of x. Now, the way I've written it here is not right? We have to do 4 times this whole thing, so we need to put that in parentheses. Okay, but then we can now distribute the 4 and get 4 times natural log of 12 minus 4 times natural log of x. Okay, so we split this apart and wrote it as natural log of 12 minus natural log of x, and we multiplied that whole thing by 4, and we're allowed to distribute the 4 now. Now the question is, what's the derivative of this? Well, 4 times natural log of 12 is really just a constant. In fact, natural log of 12, you could type it into a calculator. It's just some crazy decimal, multiply it by 4. This is really just a constant. So the derivative of that constant is going to be 0. So then what's the derivative of this? Well, the derivative is going to be 4 times 1 over x, right? Or 4 over x, and we have a minus in front of it. So this is really negative 4 over x. Okay, again, the derivative of this part is 0. The derivative of 4 ln of x is just 4 times 1 over x, or 4 over x, and we still have the minus in front of it. So it's negative 4 over x. Okay, this one you should be able to do no problem. And same thing here. These are just multiple choice ones. And same thing here, right? All these ones are pretty similar. You should be able to do them without too much trouble. Okay, same thing for this one. Remember, the derivative of negative 6 times ln of x would be negative 6 times 1 over x, or in other words, just negative 6 over x. And then you have the derivative of x to the fifth would be 5x to the fourth. So it's actually going to be part A here, right? Negative 6 over x minus 5x to the fourth. Right, notice that this part here is wrong because it's not negative 6 over x. Same thing here. There's no negative. And this one is wrong because it's not just minus 5x, it's minus 5x to the fourth, right? Remember, the derivative of x to the fifth is 5x to the fourth. Okay, this one is similar to what we've done before. So you bring the 7 out front and then take the derivative. And same thing here. And here, so again, take the 3 out front. So this part over here will really end up being 12 times natural log of x, because the 3 comes out in front and multiplies by the 4. All right, what about this one? F of x equals 1 plus natural log of 5 over x to the fourth. And it says use appropriate properties of logarithms to rewrite f of x and then find f prime of x. All right, to take the derivative of this, we're going to rewrite it as 1 plus, well, this would be natural log of 5 minus natural log of x to the fourth. Right, that's the quotient property of logarithms. And now we're going to use the power property of logarithms to bring this 4 out front. So we have 1 plus ln of 5 minus 4 times natural log of x. Okay, now what's the derivative of this? Well, f prime of x is, the derivative of 1 is just 0, and the derivative of natural log of 5 is also just 0. Right? That's just a constant. I mean, type it into a calculator. Ln of 5 is a decimal. So this is all a constant here, so its derivative is 0. Now, what about this? Well, the derivative of 4 times natural log of x will be 4 times 1 over x. All right, so we get negative 4 times 1 over x, which we can also write as negative 4 over x. Okay, notice that's answer A. Okay, now the next couple have to do with finding the equation of a tangent line. Find the equation of the line tangent to the graph of f at the indicated value of x. So our function is f of x equals 10 e to the x plus 6x, and we're trying to find the equation of the tangent line at x equals 0. Okay, well, first we need to find the slope of the tangent line at x equals 0. So how do we do that? Well, we find f prime of 0. But in order to find f prime of 0, we need to first of all find f prime of x. So f prime of x, what's the derivative? Well, the derivative of 10 e to the x will be 10 e to the x. And the derivative of 6x is just 6. Okay, now what's f prime of 0? This would be 10 times e to the 0 plus 6. Well, e to the 0 is just 1. So this is 10 times 1. So that's 10 plus 6, which is 16. Okay, so the slope of the tangent line is 16. Now we need to find the equation of the tangent line. Well, we know the slope of the tangent line. We also need to know one point on the tangent line. And it's going to be 0 comma something. Well, 0 comma what? Well, we need to go back to the original equation and ask ourselves, what is f of 0? So not f prime of 0, but f of 0. So we plug it in here. We get 10 times e to the 0 plus 6 times 0. And that ends up being 10 times 1, which is 10, plus 0. So it's just 10. So in other words, the point 0 comma 10 is on the tangent line, and the tangent line has a slope of 16. Okay, so now we just need to use the point slope formula. So y minus y1 equals m times x minus x1. Now this is our m here, and this is our x1, y1. Okay, so what we get is y minus 10 equals 16 times x minus 0. Or in other words, y minus 10 equals 16x. And we add 10, we get y equals 16x plus 10. In fact, I've graphed 10 e to the x plus 6x in Desmos, and it's kind of hard to see the whole graph. But notice it goes through this point 0 comma 10. And the slope there, what is the slope? Well, it turns out that the slope is 16. And notice the blue line there, the tangent line, approximates the curve there, right? This blue line here, y equals 16x plus 10, is tangent to that curve at x equals 0, right? 0 comma 10. I think the next example will be a little bit easier to see the tangent line and a little bit easier to see what's going on. Okay, this one should be a little bit easier to see what's going on. It says find the equation of the line tangent to the graph of f at the indicated value of x. And our function is f of x equals 7 plus 2 times natural log of x. And we're wondering what the equation of the tangent line is at x equals 1. So here is the graph of the function, 7 plus 2 times natural log of x. And the question is, at x equals 1, in fact, I think the point 1 comma 7 is on the graph here. At x equals 1, what is the equation of the tangent line, right? We can imagine a tangent line right here going through that point, having the same slope as the slope of the graph. The question is, what is the equation of that tangent line? Okay, so here's our function. And the question is, what is f prime of x? Well, f prime of x is going to be the derivative of 7 is 0. The derivative of 2 times natural log of x ends up being 2 over x. So f prime of x is 2 over x. F prime of 1, remember we're at x equals 1 this time, f prime of 1 will be 2 over 1, which is just 2. Okay, so f prime of x was this, and we plug in 1 for x, and we end up getting 2. So the slope of the tangent line is 2. Okay, so notice here at x equals 1, it turns out that the slope there, the slope of the curve, the slope of the tangent line there is 2. Now, what point does this go through? Well, you can kind of see here, the point is actually 1 comma 7. But how could we know that? Well, you just plug in 1 for x here. So what's f of 1? Well, notice our formula for f of x is up here. F prime of x is this. So we found f prime of 1. Now the question is, what is f of 1? Well, f of 1 would be 7 plus 2 times natural log of 1. Now, natural log of 1 is really 0. Right? Log base anything of 1 is going to be 0, right? Right? E to the what power is 1, right? Well, e to the 0 is 1. So this is 0. So 2 times 0 is 0, and we end up just getting 7. So notice f of 1 is 7. So we have the point 1 comma 7, and we have a slope of 2, right? So this is like our m, and this is our x1, y1. And so we're going to plug it into y minus y1 equals m times x minus x1, the point slope formula, right? We have a point here, and we have the slope up here. Okay, so this is the point slope formula. We have y minus 7 equals 2 times x minus 1. Okay, now let's simplify this and put it in the form y equals mx plus b. So we're going to distribute the 2, first of all, 2x minus 2. And then we're going to add 7 to both sides. We get y equals 2x plus 5. Okay, so y equals 2x plus 5. That's the equation of the tangent line. In fact, let's check that. Let's type y equals 2x plus 5. And notice, yeah, that is the tangent line to the curve at x equals 1, right? This point 1 comma 7 is on the curve. There is the tangent line here to the curve, right? So notice to find the equation of that tangent line, to find the equation of a line, you need to know two things about the line. You need to know a point on the line, and we know a point on the line, it's 1 comma 7, and we need to know the slope of the line. And we found the slope of the line by finding f prime of 1, right? We took the derivative and plugged in 1. Okay, so let's type in 2x plus 5. And that's our answer. Okay, this one is very similar to the one we did 2 problems ago. Find the equation of the tangent line at the indicated value. So you need to take the derivative, plug in 0. Also find f of 0, and then use the point slope equation. And this one is also similar. F of x equals 6 plus natural log of x. Find the equation of the line tangent to the graph. So again, you could graph this in Desmos if you want to kind of get a feel for what the tangent line looks like. But ultimately, you need to take a derivative and plug in 1 and also find f of 1. So find f of 1 and f prime of 1 and use the point and the slope to find the equation.